So we've taken a look at the idea of vector fields and we've taken an idea of a line integral. So now what we're going to do in the next few sections is we're going to start to take a look at specific types of line integrals. And one of those is going to be the types that are conservative. Now, if for some reason we have the idea that some sort of potential function is conservative, meaning that you can find a conservative vector field from that potential function, then what that means is that it is independent of the path, meaning that no matter which path you take to be able to go from point A to point B, as long as it's a conservative vector field, as well as the potential function for that shows that it's going to be conservative, then what you can do is you could just evaluate that potential function and be able to use something called the fundamental theorem of line integrals. All right, so essentially the fundamental theorem of line integrals says that if you know what the potential function is, then what you can do is you can integrate the force field F dot dr and find the amount of work necessary to move the particle through the force field by taking the potential function at the terminal point minus the potential function at the end point or the beginning point, the initial point. And what that's going to do is that's going to make it a lot easier for us if we know what the potential function is. All right, and we're going to take a look at how to be able to find the potential function given some sort of vector field. So just to illustrate independence of path, let's take a look at a really basic example of this. So let's say we have this conservative vector field, f. Okay, so f is equal to yi plus xj. Now later what we're going to do is we're going to show how to get to the potential function. All right, but for right now I'm saying that just verify that the potential function is xy. We're going to evaluate f dr along three different paths. And on those three different paths, we should end up with the same solution. Then we're going to use the fundamental theorem of line integrals. And then finally, if truly this is valid, then we should end up with the same values for parts B through E. So let's see what happens here. So for letter A, we're asked to verify that phi of xy is equal to xy is indeed the potential function for that vector field yi plus xj. Well, the partial of phi with respect to x is going to be y, and then the partial of phi with respect to y is going to be x. So, just like we saw in the very first section, the force field, or the conservative vector field, in this case xy, is going to be equal to yi plus xj. Right? And that's exactly what we wanted. Right? So that's how we can verify, just by finding the partials and then sticking an I and j in front of them. Now, let's find f dot dr using parameterizations for three of these. Okay, so for part B, we have a line segment. So the parameterization, we can say that x is equal to t. Since y is equal to x, that means that x is equal to t as well, or y is equal to t as well. So our r of t is going to be equal to t comma t. R prime of t is going to be 1, 1. And then we're just going to substitute t back into the function. Right, so f at r at t is going to be equal to, we said yi, so that's ti plus xj, or tj. So now we can dot the two. Remember, we dot r prime with f at r at t, and f at r at t is going to be t comma t in the component form. So f dot dr is going to be equal to t comma t dot 1 comma 1. If we dot those, that becomes t plus t, which is 2t. And now we're just going to integrate. We integrate 2t dt from 0 to 1, because that's our f dot dr. Clearly this just becomes t squared from 0 to 1, and we end up with 1. Now that's not too difficult to see. However, this should be the same thing along the other two paths. All right, so for part C, we're doing the exact same thing, except now we're doing it along a parabolic path. So for part C, we're going to say that x is going to be equal to t, y is going to be equal to the parabola, t squared. That means our r of t is going to be t squared. R prime of t is going to be equal to 1 comma 2t. And then the original vector field at the function t squared is going to be equal to, remember it was yi, so t squared I plus xj. All right. So now we're going to dot these. We're going to dot r prime and we're going to dot f. So now we end up with the integral 0 to 1, and we go 0 to 1 because the particle moved from 0, 0 to 1, 1, of, we're going to dot these, so 1 comma 2t dot t squared comma t. Right? Now technically that's r prime dot f, or dr dot f, but it doesn't matter. Okay, and there's a dt in here. So that's going to be the integral from 0 to 1. That's going to be 1 times t squared, which is t squared. 2 times t, or 2t times t, is going to be 2t squared. This ends up being 0 to 1 of 2t to the third dt, which is just going to end up being t to the fourth, or I'm sorry, t squared, excuse me, so 2t squared. We're going to add 1, we're going to divide, this should be 3t squared, excuse me. Okay, there we go. Right. And then we're just going to add 1 divide, so now we get t cubed from 0 to 1, and that just turns out to be 1, which is good because that's what we expected. Okay. Now we're along a cubic path for part D. Okay, so part D says, now we have this cubic path. So along the cubic path, let's define x to be t, let's define y to be t cubed. We know now that r of t is going to be t comma t cubed. We know the derivative is 1 comma 3t squared. And then we're going to substitute back in, so f at t comma t cubed, and that's going to be equal to, now remember it's yi, so that's t cubed I plus xj, so that's tj. And now we're going to dot r prime with f at r at t, so that's going to be the integral, still 0 to 1 because we're traveling from 0, 0 to 1, 1. F at r at t is t cubed comma t dot r prime of t is 1 comma 3t squared. We need a dt here. When we evaluate, t cubed times 1, t cubed, t times 3t squared, 3t cubed, dt, and then we can see it's going to be 4t cubed. We integrate. By integration, that's t to the fourth from 0 to 1, which just turns into 1 again. All right, so this is independence of path. No matter if we took a linear path, a quadratic path, a cubic path, because the function was conservative, then its vector field, it doesn't necessarily matter which path it takes through that vector field. It's going to be the same amount of work. All right, now, the last part, letter E, said, well, let's use the fundamental theorem of line integrals. Okay, I'll just abbreviate that, FLIT. And that means we take phi of x1, y1, and subtract from that phi of x0, y0. Well, in this case, remember we have 1, 1 and 0, 0 as our points. So we're just going to substitute those. And remember, phi of xy was equal to xy. So that means that phi at 1, 1 minus phi at 0, 0 is going to be equal to 1 times 1 minus 0 times 0, and clearly that's 1. All right, so this is our fundamental theorem of line integrals. If we have the potential function, then all we have to do is just throw those points back in, and we don't even have to go through any integration whatsoever, as long as we have the potential function from that vector field. And then I think the last part asks us to be able to make some sort of general comment. Okay, it is evident that B through E have the same results. Okay, and that's because F is conservative. All right, so the next series, what we're going to do of videos is we're just going to look at what it takes to be able to find the conservative vector field, the conservative function given or the potential function, excuse me, given the conservative vector field.